So in this video, we're going to be talking about another, we could say, a topic that falls underneath U-substitution, is U-substitution by completing the square. So this usually involves like a quadratic, a quadratic, and it's usually in like a fraction form. And in something like this, we're gonna have to use completing the square to actually simplify the integral a little, and then solve. So I basically listed general formulas of what, like, general integrals that you're gonna probably encounter when using this kind of method. So the first one is just 1 over a quadratic, right? So whenever you see something like this, think about, oh, can I complete the square here? And then the B says 1 over square root of a quadratic. And the same thing, like, you need to think about, like, okay, is completing the square possible here? And then the harder ones are C and D, where we have an algebraic function over a quadratic, and then an algebraic function over a root of a quadratic. And these can get a little complicated and a little long, so just be wary of that. But the thing is that these can be simplified. Like, a lot of integrals can be solved, and even if it's in this form, this is still like a solvable integral. We can still integrate this. It's just gonna take a bit of time to integrate it. So let's actually first write down whatever you see. So the idea here is to basically complete the square, right? And completing the square is something you should have learned in like algebra 1 or something. And this is just simple algebra that we're going to be using to simplify the integral, and then integrate using will be the new information we've learned in calculus 2. So completing the square. So I'm just gonna give you guys like a general, like, not even an intro, just like a little recall of completing the square. So say if we have the quadratic ax squared plus bx plus c, right? In order to actually complete the square, what we're just gonna have to do, so I'm just gonna say the product of whatever we get for completing the square is h. So we want to take this coefficient of the middle variable, so b. It's going to be negative b over 2a. Actually, wait. This is just let me redo this. So completing the square, all you have to do for completing the square is do b divided by 2 and then square that. And then whatever you do, you just add on both sides. So like you would just do whatever you get for b over 2 squared plus f of x, whatever f of x was, and then ax squared plus bx plus c plus whatever we get for the completing the square. So like that. And then once we do this, we're gonna get something that allows us to basically put the entire quadratic into a simpler form. So right here we would want to subtract this c on both sides, and this f of x would generally be equal to 0 when we're trying to just solve. So these two cancel, and what we're left with is just, actually no, on this side this doesn't cancel. This is just 0, right? Because when we're solving for a quadratic, we generally set f of x equal to 0, right? And then we subtract c, and we get negative c is equal to ax squared plus bx. And this is where we complete the square. Alright, we're going to add b over 2 squared on both sides. It's going to be plus b over 2 squared. And then you would add these two things. You would add the whatever you get for the completing the square plus the constant. And then the right side of the equation would turn into something like this. So it would look something like this, where you have ax minus h squared plus k. And this allows us to basically simplify the entire quadratic and make it, we can basically factor it and then actually integrate separately, because this is gonna be like that, right? So we can actually split this fraction up and actually solve for a certain, actually not even split the fraction up. There's gonna be an integral rule generally that's gonna allow us to basically integrate. So that was just completing the square. So we're gonna do an example for each one of these things. So an example for A and an example for B, and so on. So let's first do an example for case A. So let's just write that up here. 1 over ax squared plus bx plus c, right? Example. So let's say we want to take the integral of 1 over x squared plus 4x plus 10 dx, right? Now the first step would be completing the square, right? So complete square. So what we do for completing the square, we do x squared plus 4x plus 10 is equal to 0, right? Now we subtract 10 on both sides, because we only want this on the left side so we can complete the square. So x squared plus 4x is equal to negative 10. Now when you complete the square, we do b over 2 squared. B in this case is 4, right? So we have x squared plus 4x plus 4 over 2 squared. And remember, we have to add this this product, not this product, but this result of completing the square on both sides. So negative 10 plus 4 over 2 squared. So when we simplify, we get x squared plus 4x. 4 divided by 2 is just 2. 2 squared is 4. So x squared plus 4x plus 4. Minus 10 plus 4. We get x squared plus 4x plus 4 is equal to negative 6. This can be simplified into the form I was talking about, which is a times x minus h squared plus k. So let's do that. This is just simply x plus 2 and then x plus 2, right? So we can just write what we can just write is x plus 2 squared. That's all we really need. Equals to negative 6. And then when we move this negative 6 to the other side, we get x plus 2 squared plus 6 is equal to 0. So we're in that form, a times x minus h squared plus k, right? K is positive 6. A is 1, right? A is 1, and then h is let's see, h is negative 2. So now that we completed the square, now we can continue integrating. So we're gonna substitute whatever we got right here for the original quadratic. So now we can write 1 over x plus 2 squared plus 6 dx. Now this is where we're gonna be using U-substitution, because remember, this is U-substitution by completing the square. The first step is usually completing the square, and then we do U-substitution. Now, like any U-substitution problem, we basically determine what's U, and then solve. So U is x plus 2. Du is equal to 1 dx. So we can substitute U for x plus 2. So we're gonna have 1 plus U squared plus 6 plus 6 dx. But we know 1 dx is just equal to du, so we can just switch it to du. So now when we get to this point, there is no, like, we don't know, we can't just integrate this looking at this just the way it is. So based off of the integral table, there's going to be an integral for tan inverse, a form of integral of tan inverse that's going to allow us to basically integrate this. So at this point, it would be handy to have like a integral table on hand. So for this, what we're going to have to do is just rearrange this equation a little, so that we have u squared plus radical 6 squared du. So radical 6 squared is just 6. I just made it so we're in the form that allows us to use the integral table. So we're gonna get the integral of, so basically the integral of something like a squared plus x squared is 1 over a. No, actually 1 over x. Actually, wait, it's gonna be x squared plus a squared. Squared. It's gonna be 1 over a tan inverse, and then we're gonna have x over a. So that's the integral of something like that, and we're in that form right now. So what we can do now, so we know that a in this case is going to be radical 6. We know x in this case is u. So let's do that. So 1 over radical 6 tan inverse. We know that we have u over a, so u over radical 6. So we end up with this. But you see that we want to switch back to terms of x. So in order to switch back to terms of x, we just substitute whatever we substituted for u back to x. So we know we substituted, let's see, we substituted x plus 2 for u. So what we would do is basically substitute back x plus 2 into the final result of the integral. So 1 radical 6 tan inverse x plus 2 over radical 6. And then since you see we're doing an indefinite integral, there's no bounds, you need to add that plus c, because this is just a general antiderivative. So plus c, and there you go. That's the answer for this first case, right? This is how you generally do it for the first case. Now for the second case we have is integrals of the form radical ax squared plus bx plus c. So we're gonna have a root now. So when we're doing the root, it's the same process though, where we complete the square first. So let's do an example here too. So let's do the example of 1 over radical 11 minus 10x minus x squared dx. So first step would be completing the square. All right, so complete square. So we're going to be completing the square of the quadratic x squared, negative x squared, minus 10x plus 11. You subtract 11 on both sides, we get negative x squared minus 10x is equal to negative 11. Make some space here. Next thing you would do is complete the square, right? So we're going to be doing b, in this case is negative 10. So we're going to do negative x squared minus 10x plus negative 10 over 2 squared is equal to negative 11 plus negative 10 over 2 squared. Now you just simplify this a little. Negative 10x squared plus 10 minus 10x. Negative 10 divided by 2 is negative 5. Negative 5 squared is 25 plus 25. That's going to be negative 11 plus 25. So on this side, so first let's simplify the side on the over here. So we get, let's see, let's see, actually, you know, the first step we should do before doing any of this, so this stuff, before doing any of this, first we should factor out the negative, since there's a negative sign right there. So let's factor out this negative sign first. So x squared plus 10x, now it's equal to negative 11. And now let's complete the square with this, whatever's inside that parentheses. The negative sign was messing it up the process a little. So let's take out that negative and then just add it in at the end. So let's do negative x squared plus 10x, right, plus 10 over 2 squared. Right, we're completing the square for the inside, but we have to add that to the other side too. So let's add that to the other side. 10 over 2 squared. So when you simplify this, we get x squared plus 10x, and 10 divided by 2 is 5, squared is 25, equals to negative 11 plus 25. Yeah, 25. So we add 25. Now we get let's see, inside of this we have x plus 5 squared, right? Because we want to be in that form negative a, we want to be in that form ax minus h squared plus k. So we have the ax minus h squared right here, this right here, and on this side when we simplify that we get 1, we get 14. No, we don't get 14. Wait, yeah, we do. So we get positive 14, and then when we subtract the 14 on both sides, we get negative x plus 5 squared minus 14. So yeah, that's what we get for the completing the square. So actually, you know what? I think I made a little mistake when calculating the completing the square. When we got up to this part right here, since we pulled out the negative on the left side, we wouldn't be adding the 25. We would instead be subtracting the 25. Since we pulled out the negative on this right side, but we didn't pull out the negative from the negative 11, we need to actually subtract 25. So that was a little mistake I made. So the basic algebra could be where you could always mess up. The calculus part could be very easy, but basic algebra is where you can always mess up, and which I kind of did. So let's go back to this, right? We're going to be subtracting that instead. So we're going to end up with the same expression here, but we're going to end up with negative 36 here. And when we add that, we get negative x plus 5 squared plus 36. So that's what we're going to put underneath the root now. So now what we can just do, I'm going to pull this to the side. But you see, you guys should have noticed by now how long these problems can take and how much algebra is involved here. So it's better to get acquainted with problems like these, because you never know what integral you can get on a test or a quiz. So now we can just substitute what we just got. So we get 1 over radical 36 minus x plus 5 squared dx. So that's what we get right here. Now we can use U-substitution. So u is equal to x plus 5, right? Since that's inside of the parentheses. U is usually going to be what's inside the parentheses when you're doing this. So just know that. So we have du is just equal to 1 dx. So du is equal to dx. Now we just substitute for that stuff. So we have 1 over radical 36 minus u squared du. So once again, we're going to have to do something like what we did before, where we rearrange the equation so we can use the integral table. So there's an integral of there's an integral for sine inverse in the form like this. So we have a squared minus x squared. So we have something like this that gives us sine inverse x over a. So we want to try to make this into this form because it's kind of in that form. So let's do that. So let's rearrange this a little. So let's do 1 over radical 6 squared, right? Since 6 squared is 36, minus u squared. And you see it's in that form right here. And in this case, a is going to be 6, right? A is going to be 6, and in this u is going to be, x is basically u right now. So we get, as the integral of this is just sine inverse u over a. So u over a, which is going to be u over 6. And then when we switch, we want to switch back to x. So back to x. We get sine inverse. So u we said was right here, x plus 5. U is x plus 5 over 6, right? And this is just a general antiderivative, so you can't forget the plus c. Whenever there's an indefinite integral, you cannot forget that plus c. That's like a mandatory, like you have to put the plus c. So that's the general antiderivative of completing the square for this form of integral. So the next two integrals are going to take a little longer. So I'm going to do a second part to this video. So I just went over the first two cases in this video, and I'm going to make another video for the other two forms of the integral using completing the square.